In this podcast, we're going to start talking about the concept of chemical equilibrium. All right, equilibrium is basically the state where the concentrations of the reactants and the products remain constant with time. So they're not changing any longer. So when you think about kinetics, remember, we were looking at the change in concentration of reactants and products over time. And now we're talking about there will be no change. So we're going to wait until they reach equilibrium, which is when there is no change. However, please keep in mind this does not mean that the reactants and products are at the same concentration. It just means that their particular concentrations remain the same. All right, so this is a little flashback from kinetics. So when we were doing kinetics, we were looking at the initial rate of the reactants and the products, okay? So how they were changing at time initially, okay? There was a very important reason to do that, and that is because over time, they eventually reach chemical equilibrium. So we had to look at them from the beginning with kinetics because we were interested in the rate or how the rate changes over time. When we reach equilibrium, though, the concentrations are no longer changing. The rate of the forward reaction equals the rate of the reverse reaction, and the concentrations are going to remain unchanged over a period of time. Okay? So that's what's happening here when you see these flat lines. Okay? So concentrations on the Y, they're not changing. All right, and when we are talking about equilibrium, you will often see these double arrows, and that is basically indicating an equilibrium situation. All right, chemical equilibrium is a dynamic, reversible state in which the rates of the opposing processes are equal. Okay? And basically what we're talking about is any bond, so ionic, covalent, metallic, whatever type of bond we're talking about, or intermolecular force, so hydrogen bonding, dipole-dipole, London dispersion, any of those that can be formed can also be broken. So this is a constant process. So when you're looking at A plus B goes to C plus D, initially when the reaction starts, you only have A and B. So you can only have the forward reaction happening, okay? Eventually, though, you make enough C and D, and then the reverse reaction will start to happen. So A and B will make C and D, and then as you get enough C and D will start making A and B again, okay? Which means that the forward reaction will be a little slower, and the reverse reaction is speeding up at that point. Eventually, though, the rates of the A and B going this way and the C and D going that way will kind of level out, and the concentrations no longer will change, and that's when you've reached equilibrium. All right, here's a graph, another graph of that. So you have the forward reaction rate decreasing, and then the reverse reaction rate increasing as more products are made. And then when they reach equilibrium is when the two rates finally level out. Okay, so understand this is different from that first graph I showed you because we were dealing with concentrations, and now we're talking about the rates, okay? So the concentrations of the reactants and products do not have to be the same, but the rates of the forward and reverse reaction do have to be the same at equilibrium. Okay? All right. So once you reach equilibrium, it may seem like nothing's happening, but stuff is still happening. You still have a forward reaction occurring, and you still have a reverse reaction occurring. They're just happening at the same time. So no matter what, they're always going to be reactants making products and products making reactants, but at equilibrium, those changes are the same. So there's no net change overall. So there's still a lot of frantic activity on the molecular level because equilibrium is not a static process, but a dynamic process, which means it's continually changing. So the chemical reactions are still taking place, but the concentrations of reactants and products is remaining unchanged. All right, here's some analogies to think about. So in a football game, an equilibrium situation occurs when we have the number of players on the field should always be the same, and then the number of the players on the sidelines will be the same, even though depending on what play and what's going on in the game, players are constantly swapping places from the field to the sidelines. Okay, so that's the equilibrium situation. All right, another one would be like a connected fishbowl analogy. So if you had two fish tanks that were connected by a tube that's large enough for the fish to go between them, eventually you would get, if you had fish in one tank, eventually fish would go through the tube and end up in the other side. Now the fish might travel back and forth, but the number of fish in each tank will eventually be unchanged once you reach equilibrium, even though they are still moving back and forth. All right, jugglers. You're looking at this picture of the jugglers, okay? Each of them are holding one ball at a time, but it's not necessarily the same ball, okay? And the same number in the air at all times, even though that might not be the same exact balls at any given time. All right, another example would be the drinking fountain line. Okay, so there's two for this one. If you had 10 students waiting in a line to get a drink of water on a hot day, as each student got a drink, then the same student re-enters the line. This would be equilibrium, so only one can get a drink at a time, and 9 would be in line. So, and as one would move, and then the next one would get to have a drink. So the person who's getting the drink is changing, but the number is remaining the same of people in the line and getting the drink, okay? Another drinking fountain example could be if you had the same situation as the first drinking fountain, so 10 students in a line to get a drink of water. But as each student got a drink and left, a completely new student came in and entered the line, okay? So again, equilibrium situation. And lastly, another analogy is a picture of, if you picture a number of horses and wranglers that are in a corral, as each wrangler mounts a horse and then is bucked off, the equilibrium could be represented by the horse and the wrangler, and then the mounted wrangler. So horse plus wrangler separate, mounted wrangler, he gets knocked off, so that would be the reverse reaction, so it's a constant going back and forth process. Now let's think about this in terms of actual molecular level events. So I'm going to show you a few simulations just to give you an idea. All right, when you're looking at this situation, you see that you have A plus BC, and that is going to make AB plus C, and then you see that the reverse reaction is also possible. So at this point, we have 3 molecules of A, 2 molecules of BC, and then 1 molecule of AB and 1 molecule of C. Okay, so you see that we're really not having a lot of reactions occurring at this moment. That's because the temperature is a little low. So if we were to increase this temperature a little bit, all right, see if we can get some reactions occurring. All right, let's see. Any reactions yet? Not seeing any yet. All right. All right, there we go. We had a reaction occur there. All right, so now you see reactions are starting to occur, but you see that these numbers are staying relatively the same. I'm going to throw up a little graph up here. Bar graph, okay. All right, now let's go ahead and increase the number of A's that we have, and we'll increase the number of B and C's that we have as well. All right, and what we should see happen over time is eventually the numbers should remain unchanged even though reactions are continually happening here. Okay, so you see that the bar graph is changing, so we are getting some reactions. But it looks like we're maintaining pretty much this equilibrium situation of 5, 5, and 2, 2. Okay, even though they are reacting and they are continually changing. Okay, all right, let me show you a different one. All right, this is another example. Okay, so we have some green reactants and some red products. Okay, and this is the activation energy between the two. I could either increase the temperature or I could just lower the activation energy. And you will see that you have some reverse reaction happening, but you also have some forward reaction happening. Okay, and so once these amounts remain unchanged over time, which is what we're pretty much seeing at this point, because it seems like we're at a pretty happy medium of like 10, 25-ish. Okay. All right. So see, we're getting a constant back and forth of the um, reactions right now, but pretty much the concentrations are remaining unchanged. Now, this is one of my favorite examples of equilibrium would be when you're talking about equilibrium within a salt. Okay, so you have, when you throw some salts, ionic salts in water, they break into positives and negatives. Once you get enough of them in water that no longer that it's a supersaturated solution, some of them cannot dissolve and break apart anymore, you will start to see a dynamic equilibrium system between the ions that dissolve and the ions that are part of the insoluble portion. So if we just pick a little area, so if we just looked right in this area, you'll see that the molecules, the ions, are forming, reforming. So you just saw some left right there, but then you'll also see more. Come see, that one just came in. And so it's a dynamic situation. They're constantly moving around, but you still will have the same number that are dissolved and bound up here, okay? So this is an equilibrium situation between dissolved and undissolved, okay? I really like this one because it makes this pretty little crystalline lattice. Table salt, he's not quite as fun. But when you see the table salt, okay, you see there's a lot more dissolved in this one, but you see this big clump of table salt right here. And if you watch it closely, you will see that it's changing shape because the molecules are constantly in a dynamic equilibrium of being dissolved, undissolved, dissolved, undissolved. But the amounts are staying the same up here, which means we have reached equilibrium. It's a dynamic situation.